Good morning, students. Limiting case of binomial distribution to normal distribution. Otherwise, it is also normal distribution as a limiting case of binomial distribution. So both the questions are same, and see the derivation of limiting case of binomial distribution to normal distribution. See the statement: binomial distribution tends to normal distribution under the following conditions. Already you know that from one distribution to another distribution, the approximation, for that we need some conditions. So here also we have the sum of the conditions. The first one is n is very large, that is n tends to infinity, and the second condition is neither p or nor q is very small, means p and q both never be very small values. See the proof: if x follows binomial distribution with the parameters n comma p, then the moment generating function of binomial distribution is mx of t equals to q plus p e power t whole power n. So this is the moment generating function of binomial distribution. With the help of MZF, we have to prove that the standard normal distribution of its MZF. That is what you have to prove, that normal distribution, standard normal distribution MZF is e power t square by 2. You have to prove that with the help of binomial distribution moment generating function. Let the standard normal variate z equals to x minus np by root npq. So actually standard normal variate is denoted by z equals to x minus mu by sigma. So mu is binomial distribution, mu is nothing but mean of binomial distribution is np, and standard deviation means of binomial distribution is root npq. So that's why let the standard normal variate z equals to x minus np by root npq. Then moment generating function of z is, so mz of t equals to e power t expectation of e power tz. But what we consider z as x minus np by root npq. So wherever z appears, we are substituting x minus np by root npq. So here the parameters are here the constants are n, p, t. So that's why we are taking outside e power n, p, t minus. So second term e power minus npt by root npq, and the leftover is e power tx by root npq. So that's why I'm writing expectation of e power tx by root npq. So it is in the form of expectation of e power tx. Expectation of e power tx means what we can write mx of t. But in the place of t, you are having t by root npq. So in the next step, if you observe the next step, e power minus tnp by root npq into mx of t. So expectation of here available expectation of e power t, this whole t, this is the x, e power expectation of e power t. So what you have to get? Mx of t. So mx of t, in the place of t we are having t by root npq. So already we are using mx of t means this is the q plus p power t whole power n of binomial distribution. Thus no, so here we are considering that, so q plus p e power t whole power n. So in the place of t, what you are having, that you are substituting t by root npq. The next step, e power minus t, so t npq by root npq into q plus p e power t whole power. In the next step, what happened to our here n? We don't have n, but from here to here, what happened to n? So here also n available in powers. So you can write it as whole power n. Instead of here you are writing whole power n. So both the terms having the power n. The next step, e power minus tp, that's why you are getting e power whole power n. So nothing but no changes in the term. So root npq, q plus p e power t whole power t by root npq. In the next step, what you are writing, e power q into e power minus t by root npq plus q. We are multiplying this term to this term. So q into this term plus p into this term into this term. So q into first term plus p into e power tq. How you are getting tq? Here t minus tp. See the simplification. E power minus tp by root npq. First term and the second term. E power t by root npq. NPQ. So now take common e power t by root npq if you are taking common. So this term, entire term you are taking common, that's why you are getting here 1. So the extra term is here available p. So that's why minus p. So already you know that p plus q equals to 1, q equals to 1 minus p. So in the place of 1 minus p you can write q. So finally you are getting here tq. After simplification of both the terms, a power m into a power n, a power m plus n, right? So then in the next step, already you know that the expansion of e power x expansion is 1 plus x square by 2 factor x cube by 3 factor, but here you are having e power minus also, that's why here you are mentioning e power minus x 1 minus x plus x square by 2 factor minus x cube by 3 factor plus 7. By applying these expressions, so finally you are getting q into 1 minus tp. In the place of x you are having minus tp from the first term by root npq plus t square p square by 2 factorial root npq whole square minus so on. Like that you are getting the higher order terms plus p into 1 plus tq by root npq plus t square q square by 2 factor into root npq whole square plus so on whole power n. The next term q into 1 q plus p into 1 p. So q plus p minus t p q by root npq plus here t q p by root npq plus t square p square into q by 2 into square ki root ki cancel. So you are getting 2 into npq plus see here also t square p q square. Here p square, but here you are having q square into p by 2 into here also root and square both are gets cancelled npq. So from this what you can write